Machine learning has shifted from a purely academic pursuit to a massive economic driver. Major technology companies are now investing billions in infrastructure and tools to dominate the artificial intelligence market. However, the learning curve for beginners is increasingly streamlined through structured curricula that blend traditional algorithms with modern generative AI concepts. While consensus exists that deep learning often outperforms traditional shallow models, the field's scope extends beyond mere algorithmic performance to include critical implementation challenges. A key thematic consensus is the interdisciplinary nature of the field, evidenced by cross-listings in numerical analysis and control theory, as well as the growing focus on real-world deployment. Yet, a notable gap remains regarding the systematic integration of these systems into the core technical development lifecycle. Today, we are conducting a post-mortem analysis of three specific machine learning pipeline failures. We will look at data drift, model decay, and infrastructure bottlenecks. For each failure, we will discuss architectural fixes designed for scaling teams. This approach moves us away from thinking about machine learning as a one-time training exercise and toward viewing it as a dynamic, tool-centric ecosystem. The first failure mode we encounter is data drift. Imagine you have built a sophisticated credit card fraud detection system. It learns from historical transaction data where fraud patterns are relatively stable. Now, imagine a global economic shift occurs. People start spending differently. They buy more online. They use new types of digital wallets. The input data distribution has shifted, but your model still expects the old patterns. It starts flagging legitimate transactions as fraud, or worse, misses new types of fraud because it does not recognize the behavior. This is data drift. It happens because the real world is not static. The statistical properties of the input data change over time. To fix this, teams need to implement continuous monitoring. You cannot rely on a single accuracy metric calculated at the moment of deployment. Instead, you must track the distribution of your input features over time. If the distribution of transaction amounts shifts significantly from what the model was trained on, you trigger an alert. The architectural fix involves setting up a pipeline that constantly compares incoming data against the training baseline. When the drift exceeds a certain threshold, the system automatically queues a retraining job. This ensures the model adapts to the new reality without human intervention. It transforms the system from a static artifact into a living organism that evolves with its environment. Now consider the second failure mode, which is model decay. This is slightly different from data drift. In this scenario, the input data might look normal, but the relationship between the inputs and the target variable has changed. Think of a map application that predicts traffic times. It learns that a certain road is always congested at 5:30 p.m. But one day, a new highway opens or a construction project closes a lane. The road is still there, but the relationship between time and congestion has fundamentally broken. The model continues to predict high traffic, but the road is now empty. This is model decay. It occurs when the underlying logic of the world changes, rendering the learned patterns obsolete. Addressing model decay requires a strategy of continuous evaluation and versioning. You need a feedback loop where real-world outcomes are fed back into the system. If a prediction consistently fails to match reality, the model must know. Architecturally, this means maintaining a versioning system for your models. You do not overwrite the old model immediately. You run the new candidate in parallel with the production model for a period of time. This is often called a shadow deployment. You compare the performance of the new version against the old one without affecting the user experience. If the new version shows significant improvement in handling the changed relationships, you promote it. This process ensures that your system does not degrade silently over time. The third critical failure point is infrastructure bottlenecks. You might have the perfect data pipeline and the most accurate model, but if your infrastructure cannot handle the load, the system is useless. Imagine a team trying to train a large neural network on a single server. The training process takes weeks. By the time the model is ready, the data is outdated. Or consider an inference service where a user asks a question and waits 5 seconds for an answer. In a high-traffic environment, this latency causes users to abandon the service entirely. This is an infrastructure bottleneck. It limits the scalability of your machine learning operations. The fix for this lies in adopting cloud-native architecture and distributed systems. You need to decouple the compute resources from the storage and networking layers. This allows you to scale training jobs horizontally across many machines. Instead of waiting for one computer to finish, you distribute the workload. For inference, you need load balancing that routes requests to available instances. Technologies like Kubernetes have become the standard for managing these workloads. They allow you to describe what you want your system to look like, and the orchestration engine figures out how to make it happen. If a node goes down, it reschedules your workloads automatically. This declarative approach separates the complexity of the hardware from the logic of the model, enabling teams to scale without managing individual servers. Here's the thing. These three fixes are not standalone solutions. They work best when integrated into a holistic ecosystem. The field is evolving from static model training to dynamic, tool-centric ecosystems, where big tech bets on end-to-end platforms rather than just isolated algorithms. Democratization of machine learning is accelerating, with resources moving from dense academic papers to accessible, community-driven guides. But the core requirement remains a strong mathematical foundation in probability and optimization to understand generalization bounds. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.